Good afternoon. All right, let's try one more time. Good afternoon. There you go. Well, thank you all for being here today. In case you don't know, I'm Feng Shenghu, the Richard G. Engelsman Dean of Arts and Sciences, and it is my honor to welcome you to the installation of Jennifer Heemstra as the Charles Allen Thomas Professor in Chemistry. It is wonderful to see so many colleagues and members of our WashU community today in the audience. I would also like to offer my warmest welcome to everyone joining us on our live stream. Thank you for helping mark this special occasion. We are delighted to have a few of Jen's family members in the audience as well. And they are John Heemstra, Jen's husband, also a professor in chemistry, and their sons, Evan and Owen. Hi. Would you guys please stand to be recognized? Well, thank you so much for being here to join us for the ceremony. These installation ceremonies are important occasions that commemorate so much more than a medallion and a title. Every time we come together, we get to pay tribute to academic excellence of our faculty, the collaborative spirit of our community, and the incredible legacy of our donors. It is so inspiring to see how our faculty, staff, students, and supporters come together to celebrate the accomplishments of a colleague. But this camaraderie and collaboration is not unusual at WashU. I see it every day in actions, big and small. It is what makes this institution so special and what enables us to achieve our ambitious goals. We are now 2 years into the decade of arts and sciences, a period of exciting growth that will transform our school into a global model for research, teaching, and scholarship. I've been so pleased to see the incredible successes that have come from this shared vision in such a short period of time. And I know even more exciting opportunities are on the horizon. It was also just 2 years ago that I recruited Jennifer Heemstra to join WashU as a professor of chemistry and the chair of the Department of Chemistry. Jen has a stellar academic reputation. Her interdisciplinary research focuses on harnessing the capabilities of proteins and nucleic acids to address unmet needs in medicine and the environment. Her lab leverages techniques from molecular and cellular biology, organic synthesis, analytical chemistry, and material science. Her many accolades include the American Chemical Society's Women Chemists Committee Rising Star Award and a prestigious National Science Foundation Korea Award. In addition to her achievements in pioneering research, I am also inspired by Jen's commitment to creating an environment of collaboration, inclusivity, and support in our science labs and the Department of Chemistry. This is a critical component of the Arts and Sciences strategic plan, and Jen is serving as an excellent role model for the entire academic community at WashU. As chair of putting a number of excellent new faculty members into the department, some of whom are in the audience today. I just saw one over there, and some have yet to come. Under Jen's leadership, our chemistry department is reach greater heights. And there's plenty of evidence to show that. We have excellent new hires as well as significant increases in the number of applications to our graduate program in chemistry. So in just a few minutes, you will hear more about Jen's impressive leadership and scholarship from Professor Gary Patty. But for now, I would like to turn our attention to the person who made this endowed professorship possible. Charles Allen Thomas was an internationally known industrial chemist who spent most of his career with Monsanto. He established this professorship in 1976 after receiving a master's degree from MIT and a doctorate from Transylvania University. Dr. Thomas began his career developing ethyl gasoline with General Motors in Dayton, Ohio. In 1926, he co-founded Thomas and Hogwarts Laboratories, which conducted research for many corporations. When the company merged with Monsanto in 1936, Dr. Thomas became Monsanto's director of research. He moved to St. Louis in the 1940s, serving as president of Monsanto for 9 years before becoming chairman of the board. Dr. Thomas's achievements included contributions related to synthetic resins, polystyrenes, synthetic rubber, and rocket propellants. There are more than 70 patents in his name. During his time in St. Louis, he was a devoted champion of Washington University, serving as chairman of the board of trustees for nearly 15 years. He passed away in 1982. We are grateful for his remarkable scientific legacy and his enduring generosity to Washington University. It is because of donors like him that we can recruit and retain talented faculty members such as Jennifer Heemstra. And now I would like to invite Gary Patty, the Michael Antenna Power Professor of Chemistry, to the podium to share more about Jen's impressive career. Gary.
Hello, everyone. Thank you for joining us today. It's my absolute pleasure to introduce today's honoree, Dr. Jen Heemstra. Jen did her undergraduate training at UC Irvine before earning her PhD in chemistry at the University of Illinois, Urbana-Champaign with Jeff Moore. She then went on to do a postdoc at Harvard University prior to moving up through the ranks, the faculty ranks, at University of Utah in Emory. After a national search just under 2 years ago, chair of which Dr. McCarthy is here, we were lucky enough to recruit Jen to be our chair of the Department of Chemistry at Washington University in St. Louis. When we think of what defines the most distinguished professors, the list of characteristics typically includes research, education and mentoring, and leadership. We're incredibly fortunate to have Jen at Washington University because she is truly exceptional in each of these areas. Now, I don't have time to list all of her impressive accomplishments in each category, but I will briefly highlight some of her major successes in each. Starting with research, Jen's laboratory is investigating what is known as RNA editing. For context, most people have probably heard of DNA, the so-called genetic code. But for DNA to relay genetic information, it must be converted into RNA. And relatively recently, it was discovered that RNA can actually be chemically modified and that can have major effects on how genes are expressed, contributing to diseases such as cancer. At this time, however, we know relatively little about how RNA is modified, and that's largely because RNA modifications are extremely difficult to study. Now, Jen is changing this by innovating cutting-edge technologies to measure RNA changes. She's creatively took a protein and she engineered it to bind to RNA modifications, which then she can use as a readout marker. Recently, she's pushed this so far that she can now even measure RNA changes in live cells. In science, we talk about the central dogma. It describes the principles of how genetic information flows from DNA. Jen is quite literally helping to redefine this core concept, which has enormous potential, not only in basic science, but also in medicine. Among her many honors and recognition of her research, and I can't name them all, is the prestigious Mira Award from the National Institutes of Health and the Cottrell Scholar Award. The second quality on the list of distinguished professors is education and mentorship. Jin is committed to not just being an excellent educator and mentor to her own students, but improving the culture of academia as a whole. She's an outspoken advocate for wide-scale change and works tirelessly to try to reach as many students as possible. If you Google her, you will find pages and pages of videos of her giving distinguished mentoring lectures all around the world, often in student forums. But another way in which she has increased her reach is through social media, where she is constantly providing career advice. And as a testimonial of her influence, she has over 100,000 followers on X, formerly known as Twitter. In fact, she has been deemed to be one of the most influential sciences on social media in the world. What is really striking and appealing to the students is her courage. While many professors are afraid to talk about failure and doubt, Jin courageously embraces these topics and speaks openly about her struggles. Her slogan is that we do better science when we prioritize mentoring. She founded a program which has now been adopted by professors all around the world, which is called Mentor First. And among her many honors is writing a column for one of the most widely read chemistry magazines, Chemistry and Engineering News, and recognitions such as the Epstein Outstanding Educator Award. Last but not least, on the long list of Jen's many admirable talents is leadership. As I noted, Jen's been chair of chemistry for less than 2 years. Before we could even install her as an endowed professor here today, Jen's already catalyzed remarkable change in the department. Last year, in her first year at the helm, she recruited 4 new tenure-track faculty, and she's on pace to recruit several more this year. As was noted, she's also expanded the graduate program to elevate our education and research mission. We went from having an incoming class size of just 7 students a handful of years ago to having 24 students last year, an increase of more than 300%. While harder to quantify, she's also positively transforming the culture of the department and the ways in which we interact with other units both inside and outside the university. As I'm sure everyone appreciates, this is not easy work, especially while simultaneously running a premier research laboratory. However, I cannot imagine anyone more dedicated to the job of leading our department to a better place than Jen. I've learned so much from Jen about how to be a better scientist, a better mentor, a better leader, and a better person. She's an inspiration, and I'm extremely proud to call her a colleague and a friend. It is my honor to introduce her as the Charles Allen Thomas Professor of Chemistry. Thank you.
Professor Heemstra, I present you with this medallion as a symbol of this new appointment. The front reads, Charles Allen Thomas Professor of Chemistry, Arts and Sciences, Washington University in St. Louis, 1853. Engraved on the back, Jennifer Heemstra, April 10th, 2024. So here comes, and I know you'll be kind enough to share that with John, Evan.
We'll take turns.
And Owen is really the one who is going to help you if you need help. So let's. Congratulations.
It is really difficult to say anything after those incredibly kind and humbling remarks, but I will attempt to do justice to all of the things that were just said. But first and foremost among that is that I want to thank Fengsheng and Gary for those very kind introductions, and to say that while it has been my privilege to be in a position of leadership for many of the things that they talked about, it is really a reflection of the hard work and creativity and innovation of all of the people in my life. So my research group, who are the ones I will share a lot about this, who have really driven the research that we've done and driven those achievements, my friends and family who have supported me along the way, and collaborators, and especially all of those in the Department of Chemistry and in leadership at WashU who have been part of the team as we have all worked to advance chemistry and advance WashU. And I will say that I woke up today, I've woken up every day since I accepted this job feeling just a flood of gratitude. And I felt that especially today as it was a chance to reflect upon just how fortunate I am to have the opportunity to be here and to get to work with such absolutely amazing people. And so my slides will be queued up here in a second, because what I also wanted to say is that because this is really a celebration of my research group, my friends and family, turn that back one, and all of my colleagues here at WashU, I hope that that is reflected in these slides. It is certainly reflected in the title, and it is so much fun. Not by the speaker. So much fun to be here celebrating among friends and family and colleagues. So I thought I'd start with a fact that you all already know. And if you didn't know it walking in, you figured out by now that I am a very enthusiastic person. And so I often get asked, or my group gets asked, like, is she always this enthusiastic? And they know that the answer is yes. Fair? Yes? Yeah. But what many people don't know is the reason why. And that is because I have the most incredible job, right? I get to work with this amazing group of students and postdocs and postbacks and researchers, and they are so creative and driven and really, really fun, as you can see from this picture. And when I was getting ready to go to college, the advice about college in my family was A, don't spend much money, and B, go there and meet a nice spouse. The second, I achieved the first goal, the second one waited till grad school, but was worth the wait. And so when I got to college, I found myself a year in with no idea what I wanted to do with my life and my career. But through a series of coincidences, I had the opportunity to work in a chemistry research lab. And unlike many people, I was like, oh, I actually kind of liked OChem, so maybe this could be a thing. So this was me, you know, a few years, decades ago. And lest the lack of a headband and frumpy sweater fool you, here I am, right here. So here I was, right? Like a year and a half into college, no idea what I want to do with my life. But I had the chance to work in this lab, and I realized that I love building with biomolecules. This research experience really instilled in me a love. Well, it got me to know the field of supramolecular chemistry, and I really grew to love it. And so the field of supramolecular chemistry, which is really the basis for all of the research that we do in our lab, is founded on these two principles of molecular recognition and self-assembly. So I'll have a quick quiz. Raise your hand if you feel like you are already like really, really an expert in molecular recognition and self-assembly, or pretty familiar with it. I expect a few hands. Yeah, I see you should raise your hands. All right, keep your hands up. Now raise your hand if you've ever played with these, or you know how they work, right? Awesome. Well, I have great news for you. You are all mostly already experts in molecular recognition, because you know that these Lego bricks function because they have these very precisely machined bumps and holes that fit together in very very, very specific ways. And in fact, if you're a parent who's ever tried to buy like off-brand Legos, you know just how precise those bumps and holes are because you've had them not work. And so molecules are the same way. Molecules have shapes, they have functional groups, and those allow those molecules to fit together and bind to each other with essentially the same reliability as you would get with Lego bricks. And then self-assembly is just taking advantage of these molecular recognition interactions along with some creativity and a design in order to create something that is greater than the sum of its parts. So as a chemist, right, any chemist in the room can tell you that this polar bear at a molecular level is exactly the same as just a pile of Legos on the floor, or even just an amorphous chunk of plastic. But because of molecular recognition assembly, it's able to be something so much better than that. And in our lab, we have come to appreciate that biomolecules like proteins and nucleic acids are just like the coolest Lego bricks ever, right? As an example of just how amazing these are, in about a minute or so, if you wanted to, you could design 2 nucleic acid sequences that can selectively find and bind to one another. So people in my group could do about 5 seconds, way faster than me. And then they can take those and throw them into a solution with a virtually infinite number of nearly identical molecules. And those 2 molecules are going to find and bind to each other with incredible selectivity and also very high affinity as well. And there's more. Nucleic acids can do this also with things like proteins or small molecules, things like metabolites or vitamins, all of the small molecules, the drugs that we take. They exist in nature. We can design them in lab, nucleic acids that are able to bind very, very specifically to these different small molecules and proteins. And so everything that we do in our lab is really focused on the question of how we can take advantage of these phenomenal properties in order to create technologies that will benefit society. And so here's what our research program looks like. Everything starts at this common conceptual core of biomolecular recognition and assembly. Our lab slogan is biomolecules do amazing things, hence the title, right? Like this idea that they have been evolved over billions of years to have these absolutely exquisite properties that we can then take advantage of in order to do interesting things. And so from here, we just look outward and say, where is there an unmet need? Often in biomedicine or the environment. And then we bring together our fabulous team of interdisciplinary scientists, and we kind of get around, sometimes literally get around a dinner table at a retreat, and we say, okay, let's dig into this, figurative box of biomolecular Lego bricks and figure out the best way to solve this problem. And then we get to use whatever tools, whatever path that takes us down, which means we often get to collaborate or learn new things. And so I want to tell you a really quick story. It's like so hard to choose which research story to tell, but I'll tell you one really quick story of a project that started out thinking about clinical diagnostics and is now heading towards development of new therapeutics. And it's actually, Gary and I did not coordinate, but it was perfect, that intro, because it's a story about RNA editing. Right? That, when I was in high school biology, which I didn't particularly enjoy, but now I work in that area, so it's pretty, you never know. This is what I was taught biology is, right? DNA makes RNA makes protein. That's it. End of story. But of course, researchers, if you work in this field, I shouldn't say of course, if you work in this field, you know that there is so much more to it than that. And one of those extra steps is something called RNA editing. So really, DNA makes RNA, and then enzymes come in and they change the RNA, and that can change not only how much protein is made, it can even change the structures of the proteins that we make inside of our cells. And so this begs the question, what do these modifications look like? So there's actually way more of them than I could possibly put on a slide. And if I tried to, they'd be even smaller than they are. If you're not used to looking at these chemical structures, that's totally okay. The main thing is to focus in on this one in the top right that is called inosine, which is kind of our favorite modification to work with. And the question is, how does inosine end up in RNA? So researchers have already figured this out. It happens by a process called A to I, or adenosine to inosine RNA editing. And now I'm not classically trained as a biologist, so I love this process because everything does exactly what it says. So if you've learned about DNA or RNA, you know that there's 4 nucleobases: adenosine, uracil, cytosine, and guanine. And so about a fourth of it is this adenosine. And so anywhere that there's an adenosine, this enzyme called an ADAR, which is an editing enzyme, can come along. And ADAR stands for adenosine deaminase acting on RNA. And it does exactly that. So you've got, let me try and step down here. This little nitrogen, NH2, is called an amine group. So a deaminase kind of unaminates it, right? So it deaminates this to this oxygen. And the reason why this is important is that this changes the structure. It changes the way it interacts. So adenosine normally base pairs with uracil, but now inosine over there on the right has this different structure that makes a base pair with cytosine. So essentially what you've done is you've taken the Lego brick and you've kind of inverted where the bumps and holes are so that now it interacts with a different piece in the RNA. And so this has really profound impacts on biology and cells. And so not surprisingly, it's essential for development, this modification, and it's also misregulated in cancer and neurological disease and many other disorders. And so there's a lot of interest in being able to study it and control it. But as our lab got interested in this area, a really significant barrier we were running into is that there's no affinity reagents. You sometimes hear about like antibodies that, if you've taken like a COVID test on a lateral flow strip, like a Binax, there's like antibodies that recognize the COVID proteins. So we similarly needed something that could recognize this inosine modification so that we could study it. But the problem is that nobody had been able to make antibodies to it. And so this is where I get to introduce you to one of my phenomenal colleagues, who's now a former alumni or an alumni of our lab, Steve Knutson. So when Steve was a grad student, he started these projects around editing, and he was really stuck that we didn't have an antibody. And then one day he came to my office. He's like, hey, I've got this new project idea. It's already working really well. You want to hear about it? I was like, yeah, that's how research works in our lab. And he said, this is just a molecular recognition problem. And nature has solved this molecular recognition problem. There's this enzyme called endonuclease 5, or ENDO-V for short, and it finds inosine in DNA or RNA, but then it cuts the DNA or RNA. And he said, well, what if we could like repurpose this? What if we could like keep the binding, but lose the cleavage? And then we would have this like antibody for inosine. And the short answer is it works. With asterisks, a lot of failures and optimizations and really brilliant moves by Steve that I won't tell you about. But suffice it to say, for those who've seen a pull down, it works. And so what Steve was able to do is things like this, what he calls endoviper workflow, where now he can take all the RNA out of cells, pull it all together, kind of chop it up a little bit so it's ready for sequencing, and then he can selectively, actually literally using a magnet, pull those edited RNAs out of solution so that we can better study them. And when he does this on brain cells, get a lot of data from sequencing, which is great. The important thing here is that on the left is kind of the established method in each of these, and on the right is his method. And the fact that there's more blue on the left and red on the right means that using his endoviper method, he's better able to find these clinically important editing sites of interest, which means that we're also going to be more likely to find new editing sites of interest that can be used as biomarkers for the early detection of cancer and other diseases. And so this was, we were really excited by this research. And the fun thing of being in this job is that every new person who joins the lab builds upon what has been done up to that point. So this is where I get to introduce you to another phenomenal graduate student who's here in the crowd, Alex Quillen. And Alex came in and said, okay, this stuff is really cool, but in order to do all of those methods, you have to like break open the cells and pull all the RNA together. And when we do that, we lose kind of the differences between cells, and we lose where those RNAs are in cells. So Alex said, okay, well, if we've got like an antibody, we can do other things antibodies do. And one of the things antibodies do is a method called immunostaining, where basically if you have this antibody that binds to some target protein you're interested in, then you can, bind to that in cells and then kind of get a fluorescent molecule on there and be able to visualize it. So Alex said, what if we use this EndoV and we could immunostain for edited RNAs, but do it like while they're still in the cells? And I will again skip over a lot of really brilliant troubleshooting and optimization and validation that Alex did, and kind of cut to the chase on one of the most exciting results that she's gotten, which is to say, okay, if editing is misregulated in cancer, can we actually visualize that difference under a microscope? Because that's much faster than having to sequence. And what you're looking at here is healthy breast cells on the left and cancerous breast cells on the right. You may or may not be able to see the ones on the right are a little bit brighter. I'm really bad at looking at these and determining them from just the pictures, but we have it graphed there on the right. And what's really exciting is that by sequencing, we already know that the cancerous cells have about 1.5 times as much inosine as the healthy cells. And that is exactly the ratio of fluorescent signals that Alex gets. And so what that means is now using a microscope, we can see these disease-related changes in editing. And what we're really excited about is that now we should be able to develop technology where we could actually screen for potential drug molecules using microscopy in order to find molecules that could take a cancerous cell and reduce it down to the editing level of a healthy cell and thus have a therapeutic effect. Okay, so we were able to do that, and Alex was able to see the levels of editing and even see cell-to-cell differences. But what about where these RNAs actually are in the cells? So I get to introduce you to one more person, amazing postdoc, Benoit Arnold, who loves building microscopes, and came into our lab and said, hey, I can fit out our microscope to do like single molecule detection. I was like, well, I can't say no to that. That sounds really, really cool. And with that, he's been able to work with Alex using this EndoVia method to be able to actually see single edited RNAs inside of cells. So every dot you see, that kind of the big outline is one cell, and every dot you see is one molecule inside of the cell and represents one EndoV binding to an edited RNA. And so we've been able to now see things. These are very fresh off the presses data. We can see that like in this particular healthy cell line, we have a lot of that edited RNA right at the membrane. But in the cancerous cell line, it's distributed throughout, and there's like these kind of funky little subcellular structures like lines and squiggles. And the really fun thing about this is that when I go and give talks and people ask like, well, what does that mean? We're like, we don't know yet, because nobody has ever been able to see this before. But thanks to Alex and Benoit's method, now we're able to see these things, and we're doing work to try to figure out what's going on here. All right. I could go on and on about the amazing work that everyone in our lab has done, and I'll have a brief kind of prelude of that near the end. But I wanted to switch gears a little bit and bring up, this might be a triggering title if you took OChem and didn't enjoy it. But in organic chemistry, right, we talk a lot about mechanisms. And this brings up a mechanism question of, okay, if I start out here and I'm now here, what was the mechanism by which that transformation happened? And that's a little bit what I want to share about, because while I love the science, gosh, I love our science, this is the part that makes it really, really deeply personal to me and makes this such an incredibly special day. Because a huge part of this is that I just had outstanding mentors. So you've seen James, he was my undergraduate advisor, a couple of outstanding mentors in 3 conversations. There were many more than this, but James, when I was an undergrad, was like, I was like, LOL. I didn't actually say that because that didn't exist then, but I thought it. The thought ran through my head, like I would never get in, and if I did, I'd never pass. And he was like, no, really, you should think about grad school. And then so I did, and I had the privilege to go to the University of Illinois and work with Jeff Moore. And I had started to think about like, gosh, I really want to be a faculty member, but it's impossible. There is no way I could possibly do this. And I talked to Jeff once. I was like, look, I just look at what you do, and there is way that I could be doing that, right? Like you run the lab and write the proposals and teach the classes and manage the people and come up with all the ideas, and there's no way. But Jeff was so amazing in just giving this advice of like, of course you can, but nor should you expect yourself to. No one can at your, when you're still a grad student, but you'll get there. As you work, you grow every day and you get there. And so that pushed back my self-doubt enough that I went to a postdoc with David Liu at Harvard. During our postdoc, we were incredibly fortunate to welcome our first child, who actually just turned 16 yesterday. But then I had a different kind of doubt. Like, look, I so desperately want this career, but I didn't know any women who had had a baby before tenure, let alone before starting the job. There were some out there, and actually one was here, Karen Woolley, but I didn't know any of them. I was like, I just don't think I can do this. And what if I fail? And David, in his extremely kind way, was like, sometimes you just have to go for it. And it was his way of saying, look, you can choose to risk failure and have to live with that, or you can choose the certainty of knowing that you had this dream and you never gave it a try. Which of those sounds worse to you? And I was like, okay, done. And so I decided to apply for jobs. But I did this a little differently because I had this conversation happen like a month before applications were due. So I was like, oh man, I need proposals, cobbled together some proposals. They were good enough to get me a job. But I started my career realizing those were good enough to get me a job, but they're not really what we want to do. So here's me on the first day as an assistant professor, except our lab didn't look like that. It literally looked like that. That was our first lab at Utah. And I was like, and it had no windows. I was like, I've got this job and a lab. What's our research actually going to be about? And this was the best possible thing to happen. I don't recommend it to postdocs nowadays, but it's great because the answer was recruit amazing people and give them tons of autonomy and empower them, and they are going to drive the research that we do. And that has actually led to better research because the people I work with have better ideas than me, and that has led to better success in research and our funding, right? So I told you a little bit about this EndoV project, and now there's a whole amazing group of people who are working on that. We've also done a lot of work on these molecules called aptamers that can recognize small molecules. And again, just driven by phenomenal people. We have a project aimed at being able to image specific RNAs in cells. More amazing people. And I will say for any of my group, if your photo doesn't show up here, it's because there isn't one on our website yet. We even had an idea for a while. Miss Ramirez had this idea we can put these aptamers on membranes and like get water toxins out of water. And so he started that project. We've had this long-standing interest in these molecules called peptide nucleic acids that can self-assemble into and have all these cool materials properties. And again, just a phenomenal team of people, 3 of which are here today, Ellie, Cornelia, and Joseph. And we even through a series of circumstances and opportunities ended up doing education research into failure and coping and mindset. And I've had the privilege of working with 3 phenomenal postdoctoral researchers and amazing collaborators as part of that project as well. And so what we found is that different is better. But the most important day of my life came when I figured out that sometimes worse is better too. This is where it gets really personal. So if you've ever been on the tenure track or know someone who has, you know that about 5 years in, there's this thing called a tenure vote. And when I was at the University of Utah, mine didn't go as I expected. It was not positive. And I was absolutely devastated, right? I had failed. And it was the worst day of my life because not only had I failed myself, but I had failed my research group and I had failed my family. And so to sit and think, oh, I have somehow messed up and let down all of the people who matter the most to me in my life was such a difficult day. But then thankfully, I had wonderful allies who said, one of them is in the room, which is really special too, who said, no, that shouldn't have happened. And we're going to be your mentors to get you through this. And so it was the worst day of my life, but it also became the most important day of my career. I am 100% sure I would not be standing here had I not been through that day. There would be no me on Twitter. There would be no Mentor First. There would be no Jen at WashU. And so sometimes worse is better because that experience, kind of going through it, coming out of it, made me recognize I'm stronger than I thought I was. It cultivated a really just seismic shift in the culture in our lab, because on the worst day of my life, when everything was crumbling, our lab came together and said, hey, we're going to get through this together. We do great research. We're going to keep doing that wherever we go. And we are all in this together. And just getting really personal, it sharpened my focus on my faith and values and what's really important to me in this life and what I want my purpose and impact to be in this world. And as a part of that, really, as the sole output of that, was this vision for transforming academic culture. It was kind of the perfect storm, right? I realized that there needed to be change. I was very motivated to make that happen. And I'll tell you what, staring down the possible end of your career and then coming out of it will make you absolutely fearless. And so I came out of this, was like, anyone who knows me knows I've probably always been like this. So I was like, I've got something to say and a lot of things I want to do. And that is that, right, research, this is an inherently human enterprise. And the people we work with are by far the most important thing here, right? And that we can create academic spaces where everyone is treated with dignity and respect and has this environment where they can thrive. And if we value that, then we can put that into our reward structure. You know, it doesn't have to just be this nice thought or a wish. It is something that we can all choose to do right now. And through all of that, we can create this healthier academic culture that builds people up instead of tears them down. But it takes a lot of work and a lot of intentionality. And so in the kind of immediate outflow of this event, I had the opportunity, I already had a blog, so I had a chance to start blogging. I kind of accidentally found Twitter, which was always maybe gonna be a thing, but I was like, oh, I've got something to say and I can say it in 280 characters or less. I'm there. And through that had the immense privilege for about 4 years of writing for Chemical and Engineering News and really talking about all the topics in science that are really important to us, but we don't talk about often enough. But even more fun has been to see the way that this has expanded. So Gary mentioned Mentor First. This is a collaboration with my colleague and good friend Neil Garg, who's at UCLA. And we were just in a conversation about like mentoring. He was like, we need a call to action. And so what came out of that conversation was this initiative, which is really about like, hey, I wasn't really trained to mentor and lead, and maybe you weren't either, you know, science faculty, but we can all come together, we can help each other out, and we can all get better. And when we do that, everyone wins. And the people who win the most are the people in our groups. And so this was really fun. This happened during the pandemic, early in the pandemic. So we brought our groups together and said, okay, if you could like make faculty do anything, what would it be? You know, your group leaders. Oh, and I wanted to say, we launched these Mentor First groups at WashU. So it's been so much fun to be doing this work here. But our groups gave us like this amazing list and it broke down into like 7 different areas. And then we created this website and call to action where for every single one of these 7 things, there's a commitment that we can make as mentors. And then there's a bunch of really practical best practices that you can put into action. And so I want to say that one of the really, really fun things of being at WashU is the amount of support that when people in this place say we value mentoring, we value diversity, equity, inclusion, our leaders really mean it. And so we've been really excited to launch these Mentor First groups as like peer-led faculty learning communities that are happening on our campus where faculty and STEM get together and we just like talk about our mentoring. Oh, and I know I need to wrap up soon. I promise I'm almost done. Because I need to get to, you know, one more step in the pathway. So, right, as chemists, we talk about reaction pathways and multi-step reactions. And so I told you about this one. And everything was, you know, this has been a lot of fun up to this point. But the coolest by far opportunity came about a couple of years ago when I got an email from my friend and now colleague, Tim Vincevich, saying, hey, I don't know if you know, but WashU is looking for a new chair and we'd be really excited if you'd apply for the job. And what was so amazing about this is that as we got to chat, and then as I got to talk with the search committee, and then as I got to come here and visit and interview, what I realized is just how amazing this opportunity would be. I don't think I could have dreamed how amazing it would be. And it's been even more so. And so this move 2 years ago has truly been just far and away the most exciting professional experience, I think, for our group, our research, and also for me personally. And that's because as I started talking to people, this vision emerged for where the department wanted to go, where people wanted to go. And I just had the privilege of getting to steward that vision. And that looks like this, right? We said we're going to succeed by, excelling in research and teaching and mentoring, but really we're all about equipping the next generation of scientifically engaged citizens. And we're going to do that by creating the environment, right? We're going to create a really, really healthy environment so that people naturally thrive, right? If you garden, you can't make plants grow, but you can make really, really good soil. And a core part of that is that we are going to communicate with respect and transparency. We're going to make this a place where everyone is equally valued and equally respected, and where we communicate openly. And so just as one small vignette of what we've been doing comes to our graduate program, right? That our graduate program exists, right? To help students, all of our graduate programs exist to help students figure out where they want to go in their life, and then to help them be prepared to go there. Right? And so a really fun thing, I see many of our students in the audience. This is a student-led initiative. They came to us and said, we want to hear from people beyond academia about their careers. We're like, okay, we're listening. We can do that. And so we brought together the St. Louis area chemistry departments at SLU, SIUE, and UMSL and us. And the students at those universities started this Careers in Chemistry series. This spring, I have the privilege of teaching a class we're tentatively calling Thriving in Graduate School, which will be all the hidden curriculum, all the professional development you need to get off to a great start in your research career in graduate school. And really excitingly, I see many of my collaborators in the audience for this as well. We're coming together and building this out into a whole professional development program and applying for a grant in like 2 weeks. It's mostly written, so that we can actually get money to study and disseminate this. And the result of that has been this incredible growth, right? We can look at the numbers. This is from the first year that I was here, all of the amazing new people we recruited and hired. But what I want to leave you with is that what really matters is what's on the right. It's all of the people. And this idea that when we create the healthy environment, we recruit really amazing people and we give them what they need to grow and succeed. And I think that our future just continues to look brighter and brighter. And so I want to say that a huge part of the gratitude that I feel today is just for the amazing opportunity it has been to come here to work with everyone in WashU Chemistry, everyone at WashU, and to see what we've built together. And it's really a celebration of what we've built together and what we're building into the future. All right, so in conclusion, I've shown you biomolecules do amazing things, and I work with amazing people. This is our research group over the years. You can see we have this penchant for kind of thematic photos. We've got some pirates down on the left. We've got fun party hats. We have all of us trying to look serious in this castle last summer. We said sometimes in those buildings, they have like pictures of people and they look very serious. And we're like, this feels like a place where we need that photo, but some of us can't not smile. But I have to finish with a huge thank you to the most important of those people, which is my family. I mentioned this a little bit, but I went to graduate school looking for a career in chemistry. And the most important thing I came out of graduate school with was my best friend and spouse, John, who is here. I'm gonna like tear up. This is us hiking the Grand Canyon many years ago, though I think we still look the same. I'm gonna go with that. Whoever wants to challenge me on that can come and fight me. And out of that, we were privileged to welcome two wonderful, wonderful children into this world who may or may not be able to pick out by these photos. I promised them these wouldn't be too embarrassing. But the most amazing part of this journey that I never anticipated is that when you meet and marry your best friend and have two kids, that those kids become your best friends as well as they get older. And it has just been so amazing to be on this journey together. And I'm so grateful for our family, for all of the support, for all of the fun, all of the laughs, all of the tears. And so I just wanted to finish with a huge thank you to them and thank you to everyone for the opportunity to be here.
Thank you, Jen, for a truly fascinating presentation. And thank you for sharing your insights, both personally and professionally. I don't know why people say chemistry is a without class. It's so cool to me, right? So I'm a biologist. I think about cloning. If we could just clone Jen, everybody would say chemistry is truly cool. So I also want to thank all of you for joining us to recognize Professor Heemstra's accomplishments and celebrate the generosity and legacy of Charles Allen Thomas. I hope you're all going to stay here to join us for the reception back there and to offer your own congratulations to Jen. Thank you so much.